It's improbable that a motor operates on a single leg for an extended period without significant consequences. However, a series of events could explain the observed behavior without resorting to that scenario. Firstly, consider the possibility of a phase sequence error. When the aerator was initially switched off, the starter might have disengaged due to this error, which occurs when the power supply phases connect to the motor terminals in an incorrect sequence. Secondly, a delayed trip of the breaker may have occurred. The motor may have run on only 2 phases rather than all 3 due to the phase sequence issue. This situation creates an imbalance in current distribution, leading to the motor drawing a high current, approximately 15 amps, on the 2 remaining operational legs, compared to the usual 5 amps per leg under normal 3-phase operation. Thirdly, examine the potential of a partial insulation failure within the worn power cable. The cable's damage to 2 legs, where the insulation had worn away, could have enabled a small amount of current to leak between these 2 phases. This leakage would act as a partial electrical connection. Fourthly, the aerator's operation without a load significantly reduces the motor's typical current consumption. The reduced load, coupled with the partial insulation failure, could allow the motor to continue running on 2 phases without triggering the circuit breaker to trip. Fifthly, upon resetting the breaker following the initial trip, it is possible that the phase sequence error was inadvertently corrected. This correction would allow the motor to resume normal operation on all 3 phases, despite the continued presence of the damaged power cable. In conclusion, the unusual operation is most likely the result of a confluence of these factors, primarily a phase sequence error, a delayed breaker trip, the partial insulation failure, and the reduced load condition. It's doubtful that the motor was solely operating on just one leg for 16 hours. Let's delve a little deeper into each of these aspects to understand how they interact and contribute to the situation. Starting with the phase sequence error, it is crucial to understand its implications. A 3-phase motor is designed to operate with a specific sequence of phases, typically A, B, and C. If this sequence is disrupted, say by connecting B, A, and C, the motor can still run, but its performance will be affected. The motor might run less efficiently, produce less torque, or even run in the opposite direction if the phase sequence is severely altered. This incorrect sequence can also lead to increased current draw in some phases, potentially overloading the motor or the circuit. Moving on to the delayed trip. Circuit breakers are designed to trip when the current exceeds their rated capacity for a certain period. This delay is intentional, as it allows for temporary surges in current, such as when a motor starts. However, if the current is consistently above the rated capacity, but not high enough to cause an immediate trip, the breaker may take a longer time to trip, or it may not trip at all, especially if the ambient temperature is lower than expected. This delay can be critical in situations where a motor is running with an unbalanced load, as it can allow the motor to operate in a stress condition for an extended period, leading to overheating and potential damage. Now let's consider the partial insulation failure in the power cable. Insulation is designed to prevent current from flowing where it is not intended to go. When insulation fails, it can create a path for current to leak to ground or to another conductor. In this case, the worn insulation allowed a small amount of current to leak between 2 phases. This leakage current may not have been high enough to trip the breaker, but it could have contributed to the overall imbalance in the system and potentially masked the true current draw on each phase. The low load condition of the aerator is another important factor. Motors draw more current when they are under load. An aerator without a load would draw significantly less current than an aerator working to move water. This reduced current draw could have been low enough that the breaker did not trip, even with the other issues present. Finally, the act of resetting the breaker could have inadvertently corrected the phase sequence error. When the breaker is tripped, it disconnects all 3 phases of the power supply. When it is reset, the phases are reconnected in a random order. There is a 1 in 6 chance that the phases will be reconnected in the correct order. If the phase sequence error was the primary cause of the initial trip, resetting the breaker could have corrected the problem and allowed the motor to run normally, at least temporarily. To further investigate such scenarios, it is crucial to use appropriate measuring instruments and follow systematic troubleshooting steps. Firstly, a phase sequence indicator can confirm the correct phase sequence at the motor terminals. This tool can quickly identify if the phases are connected in the right order, eliminating phase sequence error as a potential cause. Secondly, a clamp meter can measure the current in each phase conductor while the motor is running. This will reveal any current imbalances and indicate if the motor is drawing excessive current on any particular phase. Thirdly, an insulation resistance tester, also known as a megometer, can measure the insulation resistance of the motor windings and the power cable. This will identify any insulation failures that could be contributing to the problem. Fourthly, a thermal imager can detect hotspots on the motor windings, bearings, and other components. This can indicate areas of excessive heat that could be a sign of impending failure. Fifthly, a motor analyzer can perform a comprehensive set of tests on the motor, including voltage, current, resistance, inductance, and capacitance measurements. This tool can identify a wide range of motor problems, including winding shorts, open circuits, and insulation failures. Sixthly, a power quality analyzer can monitor the voltage and current waveforms of the power supply. This will reveal any voltage sags, swells, or harmonics that could be affecting the motor's performance. Seventhly, visual inspections are crucial. Carefully inspect the motor windings, connections, and other components for signs of damage, such as discoloration, cracking, or corrosion. This can often reveal obvious problems that would otherwise be missed. When troubleshooting motor problems, it is essential to follow a systematic approach. Firstly, gather information about the problem. Talk to the operator, review maintenance records, and gather any other relevant information. Secondly, perform a visual inspection of the motor and its associated components. Look for any signs of damage or abnormalities. Thirdly, use appropriate measuring instruments to gather data about the motor's performance. Measure voltage, current, resistance, insulation resistance, and other parameters. Fourthly, analyze the data to identify potential causes of the problem. Use your knowledge of motor theory and troubleshooting techniques to narrow down the possibilities. Fifthly, test your hypotheses by performing additional tests or making repairs. Verify that your repairs have corrected the problem. Sixthly, document your findings and actions. This will help you track the history of the motor and prevent similar problems from occurring in the future. Understanding three-phase power systems is crucial for effective troubleshooting. A three-phase system consists of three alternating current voltages that are offset by 120 degrees. This arrangement provides a more constant power flow than a single-phase system and is commonly used for powering motors and other heavy electrical loads. The advantages of three-phase power include higher efficiency, smoother operation, and the ability to deliver more power for a given conductor size. However, three-phase systems are also more complex than single-phase systems, and they require careful balancing to ensure optimal performance. An unbalanced three-phase system can lead to increased current draw, reduced efficiency, and potential damage to equipment. Balancing involves ensuring that the voltage and current are equal in all three phases. This can be achieved by distributing the load evenly across the phases. When troubleshooting three-phase systems, it is essential to measure the voltage and current in each phase to identify any imbalances. If an imbalance is found, the cause must be identified and corrected. Common causes of imbalance include uneven loading, faulty equipment, and damaged wiring. Protective devices such as circuit breakers and fuses are essential for protecting motors and other electrical equipment from damage. These devices are designed to interrupt the flow of current when it exceeds a certain level, preventing overheating and potential fires. Circuit breakers are generally preferred over fuses because they can be reset after they trip, whereas fuses must be replaced. However, both types of devices must be properly sized to provide adequate protection. The size of the protective device should be based on the motor's full load current and the applicable electrical codes. It is also important to consider the motor's starting current, which can be several times higher than its full load current. Protective devices should be able to withstand the starting current without tripping, but they should still trip quickly enough to protect the motor from overloads. Proper wiring practices are essential for ensuring the safe and reliable operation of electrical equipment. Wires must be sized correctly to carry the intended current, and they must be installed in accordance with the applicable electrical codes. Connections must be tight and secure to prevent overheating and arcing. Insulation must be intact to prevent short circuits and ground faults. When working with electrical equipment, it is essential to follow safe work practices. Always de-energize the circuit before working on it. Use appropriate personal protective equipment, such as gloves and safety glasses. Follow lockout/tagout procedures to prevent accidental energization of the circuit. If you are not qualified to work on electrical equipment, call a qualified electrician. Safety is always a top priority when working with electricity. Improper procedures can lead to serious injury or death. In this particular scenario, the presence of multiple concurrent faults made the troubleshooting process more difficult. If the insulation failure had been more severe, or the motor had been operating under a heavier load, the circuit breaker would likely have tripped more quickly. If the phase sequence error had been corrected earlier, the motor might have continued to operate normally despite the damaged wiring. However, the combination of these factors created a situation where the motor continued to run, albeit in a compromised state, for an extended period. The key takeaway is that a thorough understanding of electrical theory, combined with systematic troubleshooting techniques, is essential for diagnosing and resolving complex electrical problems. Always consider all possible causes and use appropriate measuring instruments to gather data and verify your hypotheses. And never underestimate the importance of safety when working with electricity. Remember to consult the National Electrical Code, specifically sections like 430 for motor circuits and protection and 310.15 for ampacity of conductors, which are essential for ensuring safety and compliance in electrical installations. Also, the information about motor full load currents can be found in NEC Table 430.250. NEC Article 100 defines many electrical terms, which are essential for understanding electrical concepts and for proper and safe installation.